Hey everyone, my name is Sydney Lai, and I am going to cover a talk today about game design and how to incorporate machine learning in it. And just to give you a little bit of context, I am a developer advocate, so I absolutely love helping people learn how to build incredible experiences with their development. And to give a little bit more context, I am here with Somewhere Street, and what we're going to learn today is how Somewhere Street, we are a club, we're an organization where we co-own and co-produce games together. We are a cooperative game publishing company. So with that being said, yeah, let's explore essentially how we can design better ML algorithms. I said that weird. ML algorithms to basically enhance game theory within our video games. With that, like I said, I am a developer advocate. I've been in the space for about 10 years now, a little bit over, and I specifically have spent my career focusing on blockchain, security, gaming, and a little touch and go on the ML side. And recently, I've been really obsessed with basketball, specifically the game theory behind basketball. It is also currently, at the time of recording, basketball season. So, with that, in today's talk, we are going to cover pretty much three main topics throughout. We're going to use case studies to help you navigate how to better design ML algorithms for your gameplay and your game design. So, one, we're going to cover Nash equilibrium. We're going to talk about the concept of hawks versus doves. And then we're also going to talk about a Python game example. So, the whole purpose of this talk, if you have any takeaway whatsoever, is one, I want to help encourage you to create really, really fun gameplay. There's a lot of games that are being created, and it's typically just a copy of something else. And so, thinking about really fun gameplay, may it be in a game or in an AI application that you're building or any kind of dApps or application that you're building, really think about the fun mechanisms within that application or game. And then number two, what we're going to look at is being thoughtful in how we create this ML model. Now, and the one game that I really want to get us started with, kind of as an icebreaker, is thinking about how you play rock paper scissors, right? You guys, you'd walk around, you'd play with the player, rock paper scissors. You have essentially three combination well, you have three choices to make, and within those choices there's multiple combinations starting with nine. And really the idea of introducing Nash equilibrium is that in this payoff matrix, your matrix will determine how you are going to play the game. Now, if you probably imagine, sometimes people have a strategy of like, yeah, man, I choose rock every time. I start with rock every time, right? As an example. However, as you're playing, depending on one player or you're in a room of multiple players, you're going to probably adapt, and it's really going to decide how you then play and what the payoff is, right? How many players are in this. And so what we're going to look at right now is how a player or two players, air quotes, play randomly. And so what we have here is sigma R and sigma C, right? So sigma R is going to be player one, sigma C is going to be player two. And so if you don't choose, so this is an example, if you don't choose rock, and if you choose paper and you choose scissors, these are your likelihoods of winning. And so, for example, with player C, because this person, player R, sigma R, does not choose rock, and you don't know that player R is not going to choose rock. So you're going to have a 1/3 chance of playing paper. Therefore, this equates to you're going to have a slight a lesser chance to win, really, because as you can see here, player R is never going to play rock, um, but you don't know that. So you're going to have a payoff of about a negative 0.25% of winning. Excuse me, negative 0.25 of winning. So then we're going to look at if you are then looking at an array of probabilities or chances of you winning, and you're going to play all of the options available to you, then you're going to have a 1/3 chance of winning depending on what you select. However, when we're looking at building, let's say, a Python for loop, and you're trying to create a gameplay and a database, and depending on how many rounds you play, right? So here's an example of players not playing rock, paper, scissors. So zero chance, right? And then you have player one playing rock and not playing using paper and scissor. And then you have player two playing scissor, uh, and you can see this player who played rock wins, right? So it beats scissors, and you can see them playing multiple rounds. And then towards the end of the round, you can see the amount of times the players have played. And at the very last round, the player one decides to play rock once more, so 28 to 29. And then you can see player two plays scissors again, so from 36 to 37. So then again, the rock player wins, right? And so one important thing to think about how you are playing rock, paper, scissors as a human, you're kind of watching the competition, you're kind of just going with your gut behavior. However, as there are multiple different combinations, you at some point, you're also, depending on the complexity of the game, maybe not just rock, paper, scissors, but depending on whatever game you are designing, you want to be able to create a workflow so that your ML model has the ability to input and collect new data so that you can predict new models, as an example. Because while you might not be able to guess every single combinations out there, you need to be able to allow the data to be trained so that it can create new models within the database. And so this concept is really supervised learning, where you're able to have data sets where there's typically inputs and outputs, and so that you can train the model to have better predictions in terms of outputs uh, and inputs as well. And so we can take a look into how game theory in video games work, right? And so just then we talked about, being able to grow and scale your machine learning model. However, if you look at, for example, poker, right? You got 52 cards, 5 cards per player. There's about, 6 to 8 players. That's millions and millions of combinations. It's an insane amount of combinations. No game of poker is ever going to be the same, and you're also going to be able to play poker many times without experiencing or unlocking different types of combinations that you probably wouldn't have wouldn't have reached. And so kind of on a high level, when you're thinking about creating that for loop for Python, you want to be able to kind of loop through the probabilities, air quotes, loop through your hand and understand the possible cards that you can play and understand what plays are not available to you, right? And at the end of the day, while you might not have a royal flush, your opponents might have the royal flush, but they also might not, right? And so this is kind of the concept of being able to design and scale different types of gameplay. Now, we're going to talk about something that is a bit more tangible for me personally. I love TCG. And if you look at TCG, especially with maybe not so Magic, but especially with Yu-Gi-Oh and kind of like the old school Pokemon, not kind of the double teams right now. If you look at Nash Equilibrium again as a game theory concept, the idea is that you are trying to optimize for the winning strategy of all of the probable choices that you can create. And eventually, as you're winning games in the choice or the strategy of your choosing, you're going to start to hit the game's Nash equilibrium, where then you start to learn new ways to win because you're no longer relying on your old ways to win. And so, really, this visual diagram is just to kind of give you a visual example of tree branching, of understanding how and what paths you can win, lose, win, lose, win, lose, win, win, win. Even if you keep playing the same winning strategy, eventually you will hit your game levels equilibrium, your Nash equilibrium, and therefore it's time for you to start creating a new strategy. Now, for those who are familiar with the Yu-Gi-Oh gameplay, right, there is two opponents. Typically, it's another player, but of course, I typically actually don't play live players. I typically play AI players. I pretty much exclusively play AI players. And so when we're looking at the payoff matrix, you can either play your card face up, so the opponent knows what card you have and they can plan accordingly, or you can play your card face down, so the opponent doesn't know what you are playing, and so they're going to have to make a guesstimation, an educated guess in terms of how to either attack or defend towards an unknown versus a known. And so in the game of Yu-Gi-Oh, if you both are playing face up, you're both air quotes rewarded because you are being transparent in what you are playing. You both know what the other enemy is playing. If you're both playing face down, in a sense, you're punished because you are not given a source of information. So you have to make a decision based off of unknown decisions, right? And so there's, of course, then you have one player that plays faces down, you have one player that plays face up, and the person that plays face down actually is rewarded because they have an unfair advantage of information, whereas the player on the other side of the field who plays face up, they are punished because they become a bit more vulnerable, if you will. And so this concept is expanding beyond just trading cards as well. Of course, this is also found in battle royale type games, right? And in this type of example, you can also think of game theory in another way, such as hawkish versus dovish. And so this also determines your payoff matrix, right? What's the payoff? Am I going to have a better chance of winning being more hawkish or bullish or aggressive or offensively? Or am I being strategic by playing more dovishly, playing more, more strategically defensively? So your payoff matrix and how you play is really going to depend on if you are expecting a reward. If you know that you are very skilled, you can play aggressively, you're going to play more hawkish. If you are expecting, a lower win rate because it, if you're expecting a lower win rate, if you are playing aggressively, maybe your skills are not, quite there. You don't know how to build yet. You just can't figure out the triggers anymore. You're going to play more dovish, right? But what the game does, it really mixes. The game will introduce game mechanics to mix around the payoff matrix for the players. So at any time, the player is going to have to really redetermine how they're going to play the game. Do they be hawkish at this moment or dovish? And so the way you can see, even in this graphic example, you have a loot box dropping down. So those who are more hawkish, they're going to aggressively play and run towards uh, the loot box. The con in a way is that they are then exposed and they can be shot at and be eliminated. But then the pro is that you'll get this exclusive drop and you're going to be able to increase your offensive status, if you will, right? And then of course the changing payoff matrix is also with the shrinking map. So right here, if you are trying to not be exposed, if you're being more dovish, if you're playing more stealth, if you're hiding, there's the game designers know that, and they're going to shrink the map so that it really pushes you away from your dovish playing behavior. Now, when we look at this from a traditional game design perspective and diagram, you can see here if both players, let's say in Fortnite, or both players in Yu-Gi-Oh, are playing more defensively, more dovish, you can kind of last on the map for a certain amount of time. Maybe you have a truths, and then you both win. But of course, in both games, the game kind of requires you to not both be winners, right? And then if a player decides to play very hawkish and the other player only plays defense, you can see that the aggressive one is going to win every time. And then that likelihood really changes, especially if you guys are both aggressive players. You can even think of this as countries at war, right? Air quotes, does anyone win? But the point here is that hawk versus hawk. If you're both being aggressive, again, in the game of Fortnite, you might just destroy, of 100 players, you might destroy 99 of them, and someone's gonna have that percentage where they're more likely to win. And so, really, the concept of hawks versus doves in the sense of game design and game theory is that there's really three main forms of cooperation. You have the zero sum game, where if you're playing like the earlier example, rock, paper, scissors, one person wins. This is a zero sum game, right? The positive sum game is, there's some sort of biomedical research and it cures, the blind or something. You did some kind of medical research. It's in a way a positive sum game where everyone gets treated and no one dies from this, blind zombie attack. And then the negative sum game is if you're just playing bumper cars with if everyone's just playing bumper cars with your hard-earned Lambo, it's gonna look pretty bad because everyone just destroyed their really expensive cars, and really nobody wins. But I guess it's fun. And so, really the really, really main takeaway here is, on a high level here on the left, the idea is I really want to encourage people to make fun gameplay, really fun game theory, even if it's not a game, maybe it's an application. But the idea is you really want to have people to be able to use the application. And when you are able to create fun gameplay, you to be able to do that, you need to have thoughtful machine learning models that can also grow with the kind of the styles and the demands of the human, the human like behaviors and the human psychology of how that application is being used or how that game is being used. For those who are really interested in how to apply this on a programmatic level, you can look into NashPy. It's really great. It's a Python library for you to create two-player games. And again, games can be, in this sense, gameplay. Um, and of course, if you have any questions more about how to design games, how to really explore game theory, you can always reach out to me. My DMs are open on Twitter, and so as a developer advocate, I'm always happy to help assist you. I'm a part of Somewhere Street. We are a cooperative game publishing studio, and so we're folks who work in the industry and we learn how to build games and co-own games and co-launch games together. It's really great and fun resource, and so I highly encourage those who want to learn more on how to apply a game theory into whatever application they're building to come join us and really exchange ideas on how to build and how to scale. So thanks everyone. Take care.